anyone absent? 6, 9, 12, we're good. Excellent. So just for posterity, are we all set? Okay. So today we're going to talk about chemical reactions. He introduces 3 types of chemical reactions of the many, many other types that there are in the world. So this week you're learning about decomposition reactions and formation reactions and complete combustion reactions. And so from now on, if I just say the formation of methane, you won't need me to give you the reactants. You will just know that when we talk about formation, we're talking about forming a compound from its elements. And it's not the only type of formation reaction that there is. Sometimes you can form a compound from 2 other compounds, and that's still a formation reaction. When I say decompose calcium carbonate, I don't have to tell you what the products will be. You know that it will break down into whatever elements it's made of. And if I tell you that propane undergoes complete combustion, you need to know that there's one reactant I didn't tell you about, and that is oxygen. And it will, if it's complete combustion, it will always produce the same 2 products.
CO2, H2O.
Good. And that all of those things will always be gases, except in the case of propane, that would be a liquid, which I would tell you. But you know, oxygen and the 2 products of complete combustion will always be gases, because combustion is hot. Not a surprise. So, next week, along with the quiz on elements 41 to 60, you will be responsible for 1 each of those. And we'll go over that like over and over today, and hopefully it will not be a problem. The periodic table. I need a periodic table this week. C1. So finally explain what all of these things on the periodic table mean, although we've kind of talked about it a little bit. So, I don't have any tape today either, and I really meant to. Turn me back there. No tape. Okay, well, I guess we'll hope for the best. So, when you look at, and maybe I'll just draw hydrogen, for example, on the board, when you look at the periodic table, you see that each element has a little block on the periodic table. Hydrogen is the first element. So at the very top of its block, you see a 1, then an H, and then on your periodic table, maybe something like this, with no unit, which we all know isn't my favorite thing in the world. But today you'll finally figure out what those units mean, although we've talked about it a tiny bit. So, anyone know what the number 1 at the top there means? Okay, so Austin.
It's the atomic number, so it's order on the chart, basically, and another reason.
Atomic number. Okay, so that tells order on the chart. And does anyone else know what it tells?
How many electrons are there?
Well, kind of. Ideally, if the thing is really an atom and not an ion or something else, yes. But electron numbers can change, as you guys will find out later. You haven't talked about that much yet.
How many protons?
Protons. Okay, so we haven't really talked about the makeup of the atom yet, but as you all know from past science classes, the nucleus of an atom has 3 major components. You've got protons inside the nucleus, and you've got neutrons inside the nucleus. And then atoms also have electrons that do kind of something like orbiting the nucleus. They're not like a planet orbits the sun, although that's kind of how we pretend it happens in first-year chemistry. It's not it exactly. It's another one of those times I'm going to enough information that you can build on it later. Electrons are nearly impossible to explain, and we don't know everything. But inside the nucleus, you've got protons, which are positively charged, neutrons, which are not either positive or negative, they're neutral. And then you have electrons orbiting that nucleus, which are negatively charged. I always just draw a little negative, and I never write electron hardly. And you can see that since the electrons orbit, and every electron on the planet is exactly the same as every other electron on the planet, they trade around a lot. So this electron can zoom off, go visit the city next to us, come back, stay there, a new electron will come in and take its place. Electrons move freely. So when we talk about atomic number, your electron can go here and there, you can form ions, it comes, it goes. But protons stay in the nucleus unless we're having nuclear explosion. So the atomic number tells the number of protons. That's much easier to kind of keep track of. Hydrogen has 1. And then, of course, you all know the H is called what?
Symbol.
Chemical symbol. And you have done very well at memorizing those. And then the third number is atomic mass.
Sorry.
Does anyone know what the atomic mass actually is?
It, like, you mean, how do you find it, or?
Right, like why, if it has 1 proton, why is its atomic mass 1.01?
Well, I know the math, but I'm kind of confused now.
Okay, Lily?
Is it like how much each atom weighs?
It's an average.
Okay.
So it's not, there's not any hydrogen on Earth that has an atom that has a mass of 1.01 AMU. So the unit here is AMU, which means atomic mass unit. Because atoms are so unbelievably, inconceivably small, we're not going to use grams for them on a day-to-day basis, although Saul is telling us that we know how to convert AMUs to grams. But generally, when we talk about atoms, we're talking about AMUs because they're so incredibly small that grams don't really have a meaning for us because, I don't particularly know what a number times 10 to the negative 20 something really means. Like, I don't have the concept of that. It's such a small number. We don't work with numbers like that. But atomic mass measured in AMU, at least 1.01, is kind of something we can wrap our minds around. We can compare it to, like, carbon with a mass, atomic mass of 12.0 atomic mass units per atom. I mean, those numbers are things that kind of we get a good idea of what they mean. The atomic mass is an average, though. Not one hydrogen has an atomic mass of 1.01 AMU. So some hydrogens have an atomic mass of 1, and some have an atomic mass of more than 1. But they all have to have 1 proton. So the atomic mass average changes based on the number of neutrons also. So the atomic mass is the mass of the nucleus. So we've got protons plus neutrons. And hydrogen has several isotopes. An isotope, did you all learn isotopes this week? I'll give you a quick one then. An isotope is an element with the same, it's the same element, it has the same number of protons, but it can have different numbers of neutrons. So if you consider the nucleus of hydrogen, you might have many with just 1 proton and nothing else in the nucleus, just a bare proton, that's it. And since there's 1 proton, you get pretty close to 1 AMU. But very few have also 1 neutron in there. And then there are a couple with 2 neutrons. And so if you consider every hydrogen atom on the planet Earth, and you add up all the ones with the mass of 1 plus all the ones that have a mass of 1 proton and 1 neutron, and all the ones that have 1 proton and 2 neutrons, and then you average the mass of every hydrogen atom on Earth, because we know the probability of those that have some neutrons. Then you get the atomic mass. On average, every hydrogen has a mass of 1.01. So if we have a large sample of hydrogen gas, we can bet that the average mass is going to be 1.01, because there are going to be a few of those guys with neutrons that throw off that perfect 1 mass. So that's where it comes from. It's just an average. It's not like there is one that has that mass. They have a mass based on, most of us have just 1 proton, some of us have a neutron, some of us have 2 neutrons. But, anyhow, an average. So you start to see, as you get bigger and bigger atomic weights, that you're going to get more and more neutrons, because protons are all positively charged. Do positive charges attract each other or repel each other?
Repel.
Right, like charges, positive charges repel. So what if you pack like a, well, let's look at, say, one of these fun guys down here, like say gold. It has 79 protons in its nucleus. Do you think 79 little positive charges are happy living together? No. So the neutrons partly act as like kind of little buffers, spreading them out. And mathematically speaking, in very complicated ways, there are certain numbers of neutrons that do a good job of spacing them just right. Which is why you get specific isotopes and you don't ever see other types of isotopes. Like you see carbon with 6 neutrons, and you see carbon with like 8 neutrons, but you're never going to see carbon with like 12 neutrons, because they wouldn't do the right job of spreading out the protons. But anyhow, the atomic mass average comes from the fact that there are differing numbers of neutrons in each type of nucleus. But the biggest and most important point of today's lesson is the atomic mass tells us something else. And this is like the keeper for today, okay? So, 1 hydrogen atom has a mass of, on average, 1.01 AMU. Again, there's not a single hydrogen atom that actually has that mass, but that's our average mass for the average hydrogen atom, because a few of them have neutrons, all of them have protons. But, or maybe this is tomorrow's key point, next week's key point. I'll tell you now, since we're here. 1 mole, you haven't read the mole part yet. Okay, write this down, and then as you read all of that stuff, you'll have the key point for next week. 1 mole of hydrogen atoms has a mass of 1.01 grams. So this is AMU per atom, and it's also grams per mole. But I won't spoil what moles are. We'll save it for next week, which is very close to mole day. If anyone wants to YouTube while you're writing this down, you wouldn't want to miss all the fun of mole day, which is the day after our next class, I think. Okay, so just pop next week's lesson. Not paying attention here. The key point: AMU per atom is the same as grams per mole. That hopefully will help you with next week. Let's just go back to reading my notes and stop talking randomly. Okay, so we did all that. Excellent. Okay, so when you have a compound, like let's consider H2O, this is a molecule. And just like you can find the atomic mass by looking at the periodic table and saying, well, the atomic mass of the average hydrogen is 1.01, if you want to know the molecular mass of a molecule, you just add up all of the atoms in the molecule, and then you can find the molecular mass. So hydrogen is 1.01 AMU. There are two of them, so we'll... And oxygen has a molecular mass, if you look at the periodic table. Okay, so mine says 15.9994. You guys have a periodic table with significance generally up to the 10th place, although hydrogen's kind of different. So my 15.999 will be 16 AMU. So when I add up 1 hydrogen, 2 hydrogen, and 1 oxygen, I get 18.02. Now, we have to consider significant figures when we find the atomic mass, and one of those guys that has the 10th place on your periodic table is there, right? So if we look, this 2 can't make the 0 round up, and this doesn't have significance in the 100th place. So we can't keep our 100th place because we don't have a 100th place in one of the numbers. So we'll just find that one water molecule has a mass of 18.0 atomic mass units. What that also means for next week is water is 18.0 grams and 1 mole of water. But for now, you just add up the molecular masses. So let's try one. Everyone grab a piece of paper, or if you can do that in your head, awesome. And let's see. Ethane. Can you find the molecular mass? You need your periodic table unless you haven't chosen where I did. See if you can find the molecular mass of ethane. C2H6. Consider significant figures. I picked this one. More minutes. Is the camera working? Sort of.
Oh my gosh.
Not working.
The shadow made it super duper dark.
Oh, well, we'll just come over here. Oh, yeah, I shouldn't be allowed to use a camera. Yeah, I'll just get that back. All right. So who's got an idea where we should start? So Maddie.
So are we like writing it out on the board?
Yes, I'll write, or you can write if you want. But I'll write if you talk, either way.
I'm really bad at saying it out loud.
Yeah, if you ever want to write when I call on you, feel free to just say, I'll write that up there. But that's too small. Yeah, write really big. All right, tiny. Feels like art instead of writing when you write on the board. All right, so she's got 2 carbons, and she looked at the periodic table and found they each have a mass of 12.0 AMU. And you can just multiply if you don't want to put all those 1.01s. You can just find the hydrogens all together. Okay. So if you add 12 and 12 and 6.06, what do you get?
That's 6. Oh my gosh. That's 6. That's 0. That, and then that's 30.
Okay, so Maddie finds that one molecule of ethane has atomic mass of 30.06 AMU. But significant figure-wise, the carbon data does not have the tenth place, so she's going to round it. Okay, so then 6 from the hydrogen in the hundredth place makes it round up. So when you get your answer for ethane, you're going to want to round that because the carbon is only significant in the 10th place, so you're going to have to round to the 10th place. So 30.1 AMU is going to be the right answer for that. Does anyone have any questions about significant figures and how they're going to affect your life? Because they will. Okay. So, that's good. I think it's time to start our lab because we need to kind of start it, let it run, and then talk about it kind of as we're going. Let's consider what we have on this section. Okay. So, I'm going to have you guys look at the back page first. Hopefully we don't completely run out of space. Now the front side is going to give you directions like this. Write the objective on a piece of paper, which we haven't gotten to yet, but I'm just reminding. Then write the procedure in the third person, passive voice, past tense, and write the conclusion. So you're not going to need to write a discussion or material or even really, well, the data sections here on the worksheet. So all I want lab report-wise is objective, procedure, and conclusion. So as we do the procedure, you need to be writing the procedure somewhere.
Procedure's right here.
It is, but I gave it to you in the bossy second-person way of a teacher. You have to write it in the third-person way of what we actually did. Because, like physical science did this experiment in the simplified version last week, and they found that one group had to make some adjustments because their battery didn't work and their wires didn't work, and some groups couldn't get their test tubes in because their hands are giant. Yeah. So you may find that you have to make some adjustments to what you actually did. Let's see. Oh, and it does call for baking soda. Theirs called for salt, but I use baking soda because that's what I always do. So it says, one student should make a solution of baking soda in a large Pyrex for the class. But you will write down what Micah actually does.
Okay.
Make a solution of water and baking soda, yeah. Dump a good, generous, large amount of baking soda in. Very large. Now's a good time to put away everything you like, except your lab sheet. Maybe 60 grams, a good handful, essentially. If you actually want to put it in your hand and then dump it in.
Do we need to start writing this?
Yes, so instead of one student should make a solution of baking soda in water in a large Pyrex for the class, you write what actually happened. So what's happening?
Is he dumping all of it, or how much? Do we know?
Well, we're qualitative with respect to baking soda, so we don't need to know how much, but did you get about a handful in, do you think?
I'll probably just put it in.
Yeah. So, all right, so let's consider what people have written for that first step and see if we can make sure we're all on the same page. So what did Micah do in a third person, magically? Okay, Austin.
Baking soda was poured into a gallon of water.
Good. For a handful of baking soda was added to half a gallon of water, maybe, because it's not full if you can't see.
That's true.
Physical science used the other half last week. But I didn't put any baking soda in here. I had another gallon thing of solution in. And it was shaking. Okay. for hopefully 2 of you, so you can have groups of 2.
How much water was it about?
About half a gallon. And any group that is 2 guys with giant hands should probably
I don't have the can.
take a big beaker. Actually, I think we're spread out here, guy and girl group, so we might be alright. Give it a battery. I know.
Yeah.
I can't possibly imagine how you could hurt yourself during this experiment.
We need a battery.
How many beakers did I pass out?
So should we just work together?
Yes,
Three? Okay.
you 2. Hold on. You 2. You 2.
Oh.
You 2.
I'm standing in front of me.
What is this? You 2. And you 2. Okay. Me. Any extra batteries laying around? You guys have
The battery?
I might run one just in case somebody messes theirs up, then they can still do the end of it. But if I can't find another battery, it's no big emergency. We have lots of things here. I'm pretty sure. Oh, no, I don't, because we destroyed 1 battery last week. I forgot about that. You have to destroy the battery if you can't get the wires to work. Oh, everyone needs wires. So everyone take 2 wires and pass it on.
Should we pass around the goggles?
You should, because even if you don't wear them right now, you're going to need to wear them for the decomposition reaction, which is more dangerous, and we will do outside, because it's also really bad smelling. So, let me know if you've run out of wires or have any crisis of materials. Everyone should have 2 test tubes, a beaker, a battery, which you don't want to get wet if you can possibly help it. And you want to put away everything that your lab sheet and even your calculators, put those away. I don't think you'll need them. But phones, you don't want to get it wet. Now's the moment to put those away. So, 2 wires per group. So then, once you have your wires, don't get your battery wet, but fill your beaker pretty full. Like
This is not...
Don't take that one, if you can help it. Ooh, a battery! If your wires have some nails on them, and your nails are extra specially rusty, you might want to wipe them off. Everyone should have 2 nails. If you don't, we'll go digging. Does anyone have any nails? Did physical science completely lose all of them? Great. How could that be?
Who are those students?
Didn't check on that one, did I?
We should go find them next period.
Yeah, we have 1
Put them all in the office.
Great. Well, it will work without them, or we'll destroy all the batteries. They're old.
How full do we fill the beaker?
Well, you guys, we might have to conserve a little bit. We'll have to see. If you have, here, use this beaker, and we'll keep it try not to get the batteries wet until I give up entirely on finding nails and say everyone put down your batteries, which might have to be the case today. Alright, I'm going to do a search for nails in my bag, but barring actually finding them, then we're going to do it the fun way. Okay, so I guess pass back the wires. if you do have,
We don't have them.
you have one.
He's the worst fire ever.
There's like
You guys have a nail.
poison on the bottom.
That's okay. It's from incomplete combustion. Any nails? Not many. Alright, well, let's just get some batteries then. So what you're going to do, everyone have enough solution? Okay, what you're going to do is fill your 2 test tubes and make sure you keep writing your procedure, but you're going to fill your 2 test tubes from the beaker, and you're going to fill them all the way full. And I will try to demonstrate from the giant beaker. Ooh, there is plenty. If you need more solution, I definitely have some to spare. So if your beaker starts getting pretty empty after you fill your test tubes,
Would we
then
need some more?
yeah, you'll probably need some more. Go ahead and fill your test tubes, and then I'll trade you. So do it over the table. You're definitely going to make a mess, so you want to really try to keep all your things out of the way.
How full should we?
Fill them all the way full. So here I will demonstrate. Jen, film this demonstration, which I'm going to do over your lab notebook since you didn't put it away yet. Alright, so you get it super topped off full
That
here, like all the way full. We don't want any air bubbles because we're trying to collect the gas. So once it's all the way full, watch, I'm going to put my thumb over it, and then I'm going to dunk it in, spilling it everywhere. Now see how there's no air bubble in the top? Well, there's like the teeny tiniest maybe air bubble in the top. So we really don't want any air bubbles. So fill your test tube super full. Cover with some
Do we need more
gunk
solution?
under it, probably.
Yeah.
And
I don't think my hand's gonna fit in that.
yep, that's, if you're a group of 2 guys, you will definitely need.
Yeah, I think, see, all this is air. You don't want anything.
2 is running low on solution.
Right.
Yeah.
What do I do?
You're supposed to put your thumb on it and then quickly flip it over.
And then shove your whole hand under so that. You have a small beaker.
Ah, dang it.
My hand's there is a small beaker. But I try.
I wonder if it's full enough.
Help, says Jenny. Help.
I'm too big.
Oh, you guys have big test tubes too. You'll collect more gas in
That's
there.
enough.
Ah.
Nope. It has to be complete. No air. So, yep. It might take multiple tries in a big mess, and that is normal. Multiple tries in a big mess.
Wait, do you like the small hands? You can do it for us.
I can try.
No, we don't have our soap.
Yeah.
It's okay, just fill them back up and keep trying until you get it. Yeah.
What do I do? What do we do
Fill
with
it
this one?
Oh, yeah, that has the tiniest one. So what you want to do, if you do have one that's good and one with a little air bubble, you want to put the air bubbly, the bad one, on the little end of the battery.
This one's gonna be
Is
worse,
that
I think.
good?
Is that okay?
It's got one little.
Yeah, that's okay. If you can get the other one better, that'd be great. If not, it'll
I
probably.
cannot put my hand in there. I need someone else to, probably. I guess maybe like this.
Use your thumb. Your thumb will be lighter.
Here, try it once in the big beaker, just so you get the experience, and then.
Doesn't work.
Yep.
Nope.
Once it's done,
Getting the water level higher. Yeah. I think we need more water.
Or should I try?
Here, why don't you 2 try the big beaker, and I'll just redo it with the little one. You need more? It's okay. You know, it's really a skill that takes 6 years of teaching chemistry to master. Yep, that'll do.
Do you have like a paper towel?
You guys do it.
Oh, pass the paper towel roll down the way. Alright.
Oh, bubble. I have a big micro
Well,
one,
she said
probably
it's
1
okay.
millimeter in diameter.
Oh, I
Killed him, I think.
I need my test tube though.
bubble.
No, that's really good. Wouldn't hurt to try again. Oh, surface tension. Look at that, guys.
Woo!
Alright, wow. This is like... Alright, here you go. Did anyone do that experiment in like physical science where you have to figure out how many drops of water you can put on top of a penny? Oh, see. No. That isn't good.
Man. I don't know how many tries this is gonna take.
Sorry. I can't even tell it.
If I don't do it 20 times.
If you don't get it, I'll give it.
Okay, I don't. What is a double?
No?
It looks like it for like half a second. I don't know what I'm doing wrong.
Have you tried doing it slowly and like making sure it's underneath?
So, see how my
So,
thumb
like,
is like
throwing it.
pressed here? Well, I can't do it there. And I don't want to do it there particularly because it would be kind of a waste. Alright. And I'm very likely to fail in this big one. Can you keep that one aside? Yeah, you guys, this is hard. It's not awesome, but... My thumb's too small to cover the opening.
Try to use your index finger instead of your thumb.
My index finger's small.
Yeah.
So it's
You like
acceptable or
I'll-
no, not really?
That one will do. Austin, hold on. I'm just going to do this for you guys. And you use this one while I fiddle with that one so we can get on with it. Okay. No, I can't do it. Try this. Can you not do this one? You tried this one.
Okay, yeah, it's
No, I
like
can't
this
either.
is the whole thing.
No, it's not. Screw this up.
Alright.
Thank you.
Willingness to make a mess. Okay. So now, everyone's going to take your battery, take the tape off, write your procedure, keep writing procedure. You're going to take your battery, take the tape off, and stick it down in the beaker. And we're wasting batteries. That's okay, because they're all last year's batteries.
I'm not exactly sure I want to do this.
You will not get a license.
Files will
And then try to
It's
put the test
perfectly
tubes
safe.
over.
shove it underwater.
Yes, if you have an air bubble, put that test tube over the small end of the battery.
What if you have two air bubbles?
Put the worst one over the small end of the battery. Or redo it, but it's fine.
I don't know if we can do it.
Yeah?
Yeah.
Alright, put it in. And then you don't want to... Alright, so you can see the reaction starting. Alright, and you might want to just grab some little
Do we add
thing
more water
to
before we
stack them
try
up.
to move it up over? Or do I have enough room?
You probably do, but it never hurts to have a good, solid amount of clearance. I find that scissors and rulers and
Yeah, just
combs and all kinds of stuff work well to prop up this experiment. Or, you know, okay.
That doesn't work.
Pens
What's
with
the
little
thumb supposed to
grippy
do?
handles.
No.
And two bubble batteries towards the edge.
What's the comb supposed to do?
Just prop it up.
Not
You have
popping.
huge ones, right? Hold on, we'll find you something else. Here, fill it all the way so there's less solution in there. Anyone else need more solution? holding down clumsiness. Alrighty.
I can just hold that.
It's so pesky, it'll be like a long thing. Yeah, don't bump your teeth. And kind of mind your stuff. I have a ruler that breaks really awful. Alright, so keep writing procedure. Here, Lily, try this one. This might hold it up for you. We're near the beginning, so if we drop it, it'll be alright.
What are these two cards called? Like, what do we...
Okay, so I would call the part the positive end of the battery and the negative end of the battery. The positive end of the battery is the small thing, and the negative end of the battery is the big thing.